the recording. Okay, well, as usual, there are some problems with the tablet. I'll try to sort them out. Well, I think I know what's happening. By the way, if the blinking disturbs you, please let me know. I'll turn off the camera. I don't know why the screen is blinking. I don't think this is related to the tablet, although I'm not sure. Okay, it looks like the tablet's on. Well, let's briefly recall the statement of the theorem. We have a nice morphism of the homology groups where the left-hand side and the right-hand side are something we talked about 2 weeks ago. Let's see if we remember anything about those two objects in this equality. Well, let's start with the right. No, with the left-hand side, it's easier. Well, this C infinity is well, C infinity is the space of all surfaces which live in R infinity, and the surfaces are required to coincide with some so surfaces of so we start by considering surfaces of a fixed genus G with one boundary component. Now we then require them to have the first coordinate from minus infinity to G, and we fix the behavior near the boundary so that we can append so we can append a piece of genus 1 with 2 holes and get something in something which is an element of the next space CG plus 1. Then we stabilize, and the result is the same as the classifying space of B well, let me put a pi naught here. As we mentioned earlier, this doesn't really matter for G greater than or equal 2. Why? Because the classifying space of the identity component is contractible. So let me put this pi naught in blue. Okay, now do we all remember what the left-hand side of the equality is? I think the answer is yes. If it isn't, please let me know. Okay. Well, what about the right-hand side? Well, let's. Let's recall it as well. Well, the right-hand side is also some kind of limit. Now, the AG stands for a fine Grassmannian. The plus stands for 1 point for the 1 point compactification. Now the omega denotes the loop space, and the limit is taken by mapping the suspension of the nth space to the n plus 1th space, and these are obtained from by observing that AGN plus is the Thom space of the universal quotient bundle. Not the universal bundle, the universal quotient bundle on the Grassmannian GN2. And by the way, 2 is irrelevant here. We may as well consider any dimension. Okay. Do you want me to review this in more detail or not? Well, probably. Well, if let's say the answer is no, but if it isn't, again, don't keep it to yourself. Let me know.
Sorry, but okay. What is the universal quotient bundle you said?
Well, so we have E of gamma n, which is a vector bundle over gamma n d, which is the same as gamma d of Rn. Well, since we consider oriented manifolds, we need to put a plus here, but this plus is not the same as this plus. This plus means the vector subspaces are oriented. Okay, so the universal bundle, there is a universal bundle over the Grossmanian, but this universal bundle is a subbundle of the trivial bundle. And the quotient is the universal quotient bundle.
Okay, thank you.
So A plus M D is the Thom space of the quotient bundle. Okay, now are there any more questions? Okay, well, let's try to prove the theorem. Okay, we start by then I'll go back to using the black color. So we considered the space of smooth oriented manifold submanifolds of Rn. And let's also assume that these are closed. We include the empty manifold as well, and the empty manifold will basically be the base point when we need the base point. We need to topologize this the space because in a minute we will see that the space Cn is basically a homotopy equivalent to A and D plus. Let's topologize the space. We consider we specify a basis for the topology, and then we basically take the topology generated by this basis. So we as a basis, we take all sets CBV. But what is CBV? What is B? B is simply a closed ball of some radius about the origin. No. What I wrote is not quite accurate. So I will okay. I consider submanifolds which are transversal to the boundary. What does this mean? And closed submanifolds which are transversal to the boundary. What does this mean? Well, this means the intersection, the boundary of the boundary of each submanifold is the intersection with the boundary, and the intersection is transversal. And the open sub this time the submanifolds are closed, which means they are compact, and we basically consider the usual C infinity topology on those on the space of those submanifolds. Okay. Well, I didn't say anything about the dimension of the manifolds involved. So we fix the dimension. and we assume that the dimension is greater than less than the dimension of the ambient space. There's a remark. The space we've just defined is path connected. Why? Well, suppose I have an element of Cn. There's a submanifold of Rn, which is closed. Now, and suppose I also have the T from 1 to infinity. And I take this coupled to the result of applying the result of applying the homothetic. I'm not sure how to pronounce this word in English. Which is the same as expansion. With center outside M, and scaling factor equal T. So we'll get a path or a kind of a path on the this this map the limit of this map is the empty set as t goes to infinity. Y because the intersection with every ball is eventually constant. Sorry, eventually empty. Well, constant, yes, but also empty. Okay, so the map is continuous, which means we can join every element with the empty set using a continuous path. Does this make sense?
Yeah, but I still don't quite understand how the space is topologized. So.
We in point set topology we can take any family of subsets and then take the generated topology, which means the smallest topology which contains a given family. Let's take this set as our family of subsets, and then take the smallest topology which contains this family. Now, what does this mean if we want to consider continuous maps into the space? A map is continuous if and only if the preimage of every element of the family is open. And sorry, yes, there's one thing which didn't say properly. So we I said what B is, and I said what V is, but I didn't say what CBV is. So let's say it's the space of M inside Cn such that M intersected with B is inside CBV. Does this make sense?
So on one hand, you mean by CBV this collection, and then on the other, CBV is just continuous maps.
No. Sorry. I messed it up again. Let me raise here. It doesn't make sense. Okay. Let's see. M intersected B belongs to V. So we if we have fixed B and V, it makes sense to consider all submanifolds of Rn such that the intersection with B is in V, and then we declare this the subset such that to be CBV.
I'm sorry, can you repeat what is V? Because now I don't understand.
V is an open subset of the set of all apply submanifolds of the ball such that in the intersection with the boundary is transversal and also the boundary is the intersection with the ball. So again, we now consider submanifolds of the ball. What is V? We require those submanifolds to intersect the sphere, which is the boundary of the ball, transversally, and we also require that the boundary of those submanifolds, if they have a boundary, should be the intersection with the sphere. Does it make sense?
On the one question, how do we topologize the set of all C infinities of manifolds?
Well, let's think. How would you topologize the set of all C infinities submanifolds?
Well, I have a guess here. We can use the Whitney topology, but I'm not sure if that's what you mean.
Well, well, there are several equivalent ways, but which one is the most straightforward? Well, I think the most straightforward is the following one. Suppose I have let's take a compact metric space. Then there is the Hausdorff metric on the set of all compact subsets, which is which is good news, but we want to take all derivatives into account. So how do we do this? Well, there's always the jet bundles. So for every submanifold, we basically we fix Rn inside. Over Rn, we have the bundle of germs of some fixed degree, germs of submanifolds of some fixed degree. Now, this is a finite dimensional bundle. If we have a metric on Rn, we get a metric on the jet bundle, and for every submanifold of Rn, we have a submanifold of the jet bundle of the same dimension, and there we can consider the Hausdorff metric. And we take these, we take the corresponding open neighborhoods, and we take those as elements of a basis for our topology. Two questions. Question one: does this make any sense?
Yes.
Question two: would you like me to write this all down, or what I've just said suffices? Так, хотим ли мы сейчас подробно описать топологию Уитни, значит, в компактном случае? Или хватит значит, устных рукомахательных объяснений, которые только что прозвучали? Well, all things being equal, I would suggest we move on. But let's, on the other hand, if none of what I've just said makes sense, let's not be in a hurry. We're not in a hurry. We'll go through it in detail. So, what do you think? Okay, so nobody is saying anything, which means we move on. Okay, now, so basically in the compact case, all these topological questions, point set topological questions become much more straightforward than in the non-compact case. Reducing everything to compact submanifolds does simplify things a lot. Okay. Does this part make sense now?
Yes.
Okay. Well, let's describe the homotopy type of the space CN. My claim is that CN deformation retracts onto A and V plus. Well, let's see why why this is said. Well, let me take the I want to construct a deformation retraction, and basically the idea is the same as the one we've just seen when we observed that CN is path connected. I want to rescale. I want to rescale the manifold so that only only a very small part of it survives, which will probably be some tangent plane at some point. Well, how to make this more precise? Well, let's let's take an element M of Cn, which is the same closed submanifold of Rn. And let's take a tubular neighborhood and of the manifold, which means sufficiently small, which is the same as a sufficiently small neighborhood with respect to some fixed metric on. No, it's in the non-compact case it's more complicated. But anyway, does everyone understand what the tubular neighborhood is? Okay, so I will recall it, but I will not write anything down unless people want me to. Suppose I have a non-compact or possibly non-compact manifold. I take which is the same, which is still a closed submanifold of Rn. I can take the normal bond. Then I take a function which decreases sufficiently fast, a function on the manifold which decreases sufficiently fast as at the infinitive. And then I take the exponential of the normal bundle multiplied by this function, and this function should be a smooth function from the manifold to the positive real numbers. And then I get something. I get a neighborhood which deformation retracts onto the manifold itself. If the manifold is compact, there is no need for complicated functions. We can take just a sufficiently small constant function. Otherwise, we choose a function that goes to zero sufficiently fast at infinity. Okay, does this explanation make any sense whatsoever?
I guess I have only one question. You told that we consider only closed submanifolds. Does it mean
closed,
that
but not necessarily compact?
Yeah, I'm just always confusing these two. So I thought that closed like manifold is compact, but
yes, closed in the point set topological sense, which means they're closed subsets, but they're not. They may have boundary, and they themselves may or may not be compact. Okay, so we use the same idea as on the previous page. we rescale Rn from the origin by a factor of lambda, which is a real number greater than or equal 1 or infinity. And and we also have M, and we also have W. So let me illustrate this. So I have M, now I take W. Now, if the origin does not belong to W, then I rescale I just take the rescaling by a factor of which varies from -1 to infinity. Now, if the origin is inside W, then I rescale by different factors in the normal direction and in the tangent direction. So in the tangent direction, I again take rescaling from by a factor which varies from 1 to infinity. But in the normal direction, I rescale by lambda, which is from 1 to t, where t t is t is undo, t is infinity on the boundary, and t equals 1 on m. Basically, the closer I get to m, the less I rescale in the normal direction. The closer we get to m, the less rescaling there is. In the normal direction. So we again, if we are far from m, then we rescale in all directions from 1 to infinity. If we are close to m, we only rescale by we only rescale in the tangent directions, but not in the normal directions. And this is okay. This is all we do. Now, does any of this make any sense? If we take an element of ADN, we basically what happens when we take an element of ADN? In other words, what happens if M is in a fine plane of dimension d? Well, if the plane is if the plane passes through the origin, nothing happens. The plane just stays still. If the plane is far enough from the origin, it converges to the empty set, and if we have a plane which is sort of close to the origin but not too close, then it moves a little, but it remains it moves a little, but it remains in a fine plane. Let's and by the way, it doesn't just remain in a fine plane. It remains sorry. So again, let's see what this procedure does to affine planes. Close, if we are close to the plane itself, we only rescale in mostly in the tangent direction. If we are on the plane, then we only keep the tangent rescaling, and otherwise we don't do anything. Let's say the claim is all planes when we apply this procedure, all d-dimensional to m equal a d-dimensional plane, nothing happens. The plane stands still. Now let's think a little about this and see if we agree. Okay, do we agree? And there are quite a few things which have been swept under the carpet in this argument. Okay. Maybe we'll come back to it in a minute, but first, does any of what I've just said make any sense?
Can you maybe repeat once again what in principle happens to a given submanifold? So what affine subspace corresponds to a given manifold? To every submanifold, we okay, let me try to
let me try to think how to. Let's okay. Let's try to think what actually happens as we do this procedure. We keep so what remains of M is some something. If the origin does not belong to the tubular neighborhood, then the something is nothing, the empty set. If the origin belongs to the tubular neighborhood, then we can project the origin onto M, and we get some point inside M. And my claim is what remains is the tangent subspace at this point. Okay. I will. No, it's all vanished. Okay, I will use another color. So M.
By the way, do I understand correctly that we actually need a bit of different notation for the CN? We need some like CMG to denote the dimension.
Yes, yes. The dimension is always there.
Okay.
So under the retraction, M goes to the tangent space at the point Y, where Y is the projection of the origin onto M. And if this happens if 0 belongs to W, if 0 does not belong to W, then M goes to the empty set. Okay, so yes, some of the previous remarks may have been confusing, and they probably were. Here is the explanation of the retraction, and then we join this with when M is a plane, then if the plane is far away from the origin, it goes to the empty set. If the plane is not too far from the origin, it goes to itself. And basically, how exactly far is far away, it depends on how we choose the neighborhood W. the neighborhood W can be made to depend continuously on M. So we choose a continuous family of trivial neighborhoods, and it doesn't matter which one we choose, and we choose some, and then we use. Does this make any sense?
Yes.
Okay. Okay. Now we want to introduce a filtration on Cn. We set C and K to be the set of all elements of Cn such that M inside Cn such that M is in fact inside Rk cross 0, 1, n minus k. So, in other words, the last n minus k coordinates must be bounded, and well, for the sake of definiteness, we require them to be from 0 to 1. Well, remark, if I have M inside C and K, then the projection from M to the first K coordinates is proper. Basically, the reason is the projection M is closed in Rn. So M is also closed in Rk cross 0, 1, but this time I consider the closed interval. And the projection from the product Rk across the closed interval to Rk is proper, M is closed, and so the restriction of the projection is again proper. Does this make any sense? In particular, does everyone remember what a proper map is?
Yeah, but just having some. Oh, so it's C and K, or it's just C and M.
C and K, and the last one is C and N. So for the last one, we don't have any conditions, and for the first one, we require all coordinates to be bounded. So all, in particular, elements of CN0 are compact.
Yeah, okay. So that was precisely my question. Thank you.
Okay. Now we want to define a map from C and K to the loop space of C and K plus 1. And when I don't mention the base point is the empty set. Okay, so I take manifold inside C and K. In particular, the last n minus k coordinates are from 0 to 1. Now I take the k plus first coordinate, which is from 0 to 1, and I translate the manifold in this coordinate from minus infinity to infinity. So for every element from minus infinity to infinity, I get some translate of m. And this translate will this time live in C and k plus 1, because the k plus first coordinate will be basically anything from minus infinity to infinity. And the limit as the parameter goes to either minus infinity or plus infinity is the empty set. Using the argument we already saw when we claimed that Cn is path connected, and the reason basically is the intersection with every finite pole is eventually empty, and so we get not just a path but a loop, and we get the map from C and K to the loop space of the next space. Now there are two things which happen. And I will write them down, and then we'll have a break. So if k is greater than 0, then the map we've just constructed is a homotopy equivalence. And when k is 0, things are more complicated. Namely, this map is only a homology equivalence. And even that is only true after we let n, and after we take d equal 2 and let n and the genus go to infinity. We'll talk about all this in more detail after the break, and probably next time too. Okay, so are there any questions?
So I have a technical question. What kind of a loop space is it? Is it a Moore loop space or just a regular loop space?
Well, they're all homotopy equivalent. Here we basically consider the regular loop space, but instead of maps from 0, 1, we consider maps from minus infinity to infinity, which have both limits and such that the limits go inside.
Okay.
But we will be considering more spaces and their relatives in a minute, or maybe not in a minute, but in half an hour or so. Okay. Are there any more questions, criticism, suggestions, and so on? Okay. Well, in this case, let's have a 20 minutes break, and then we'll continue. Okay, so Well, first of all, recall that a monoid or a monoid in sets is a set with a binary operation, which is associative, has a unit, but may or may not have inverses. If we have a topology on the monoid and the multiplication is continuous, we have a topological monoid. And basically, the definition is exactly the same as for groups. By observing that in the definition of in the definition of the classifying space via synthesis, we didn't really use inverses. We'll talk about the classifying spaces for monoids in more detail at some point, but let's topological monoids. If I have one, then I can form the classifying space And there is a map from from M to omega Bm, and this map is a homotopy equivalence. Well, there's a necessary condition for the map to be a homotopy equivalence. Namely, in the right hand side we have omega of something, and the binode of omega is a group. Why? Well, because omega is an H space. So we need, in order for this map to be an equivalence, we need binode of M to be a group, and this is also a sufficient condition, by the way, this is another topic for a talk, or maybe it's well, maybe it would be better to include this in the talk about the group structure theory.
I'm sorry, I missed this. We're now considering topological monoids, right?
Yes, so we take M to be a topological monoid. Then we have an induced operation on phi naught of M. But phi naught, it's just a priori, it's just a set, and there's well, if M is a topological monoid, then phi naught is also a monoid, but it doesn't have to be a group. If it happens to be a group, then the map is a homotopy equivalence. And in fact, this map is not exactly an isomorphism of H spaces, but it's essentially an isomorphism of H spaces. Of course, there's the problem with the multiplication on omega, which is not associative on the nose, and on the other hand, for M, the multiplication is associative on the nose. Well, the short answer is one can define one can define a larger and in some sense more sensible class of equivalences for monoids, and in which case M and omega Bm will be an equivalence of H spaces. There's I will not say any more about this, except I will mention the phrase A infinity. But I don't want to get into detail on about A infinity spaces and their relatives. Okay. Now, and by the way, we will not need it. All we will need is an equivalence of on the level of spaces, not H spaces, and on the level of spaces, it's not too hard to prove that we do indeed have an equivalence if pi naught is a group. Okay. Now. Let's recall that before everything vanished, before the nodes vanished, we did define the spaces C and K, where C and K is the space of all submanifolds submanifolds of Rn, such that the submanifolds are closed, meaning they're closed subsets of Rn. And the last n minus k coordinates are between 0 and 1, and the rest are arbitrary. Now, is C and K a monoid? Well, not quite. By the way, what is the operation? The operation is induced by juxtaposition in the k plus first coordinate. Well, what does this mean? Well, this means suppose we have two manifolds such that they both belong to C and K. Let's compress both in the k plus first coordinate, such that this coordinate is not just from 0 to 1, but from 0 to 1/2. And then we put the second manifold on the left of the first manifold, and we get something. We then take the disjoint union, and we get something with the n plus first coordinate from 0 to 1. This is not quite a monoid. Why? Well, because the product is not sensitive on the nose. It's only sensitive up to homotopy. But there's same as for loops. There's a strictly associative version of the same monoid. Meaning we let the k plus first coordinate to be not necessarily from 0 to 1, but from 0 to something. And the something is a positive real number, which may vary from 0 to infinity. And then the juxtaposition operation becomes associative on the nose. Now, does this make sense, or would you like me to write this down in more detail? Saman, do you know what the Moore space is?
Yes, I do.
Okay, Mark.
Можно вопрос еще раз, пожалуйста?
Марк, вы знаете, что такое пространство петель Мура?
Пространство петель Мура,
Да.
наверное, все-таки нет.
Значит, Гриша, вы знаете, что такое пространство петель Мура?
Я спросил вопрос про пространство петель Мура, так что, скорее всего, да.
Хорошо, тогда, Гриш, значит, вот попробуйте объяснить Марку, что такое пространство петель Мура.
In English or in Russian?
In English.
Okay, so the difference between the regular loop space and the Moore loop space is that instead of parameterizing loops by intervals of length 1, as we do for usual loops, we allow the parameterization to be of arbitrary length. And this allows to define a strictly associative composition of loops, because we just add lengths of two loops and we obtain a third loop of the length, which is the sum of lengths of the two loops that we compose. So that's basically a homotopy equivalent to the usual loop space, but the difference is that now the multiplication is not associative up to homotopy, but strictly associative.
Okay, Mark, does this explanation explain anything?
Да, спасибо, понятно.
Okay, Vladimir.
Да, все понятно. Ты встречал раньше.
Okay. We could use the same strategy for submanifolds, and we get a strictly associative monoid out of the space C and K, which is not strictly associative. And we call the result M and K. And next time we will prove the following proposition next time. If K is greater than 0, and this is important, and D is arbitrary, but again greater than or equal 0, then by node M and K is a group. And so we can form the classifying space of the resulting monoid, and we can claim that B M and K is the same on the one hand, it's the same as no, okay. First of all, I'll write what we will prove, and then we'll see what follows. The classifying space is the same as C naught homotopy equivalent to C naught and chi plus 1. And as a corollary,
I'm sorry, what is C naught?
C naught, which is a component which contains the base point.
Okay.
Namely the empty set. Okay, so corollary. C and chi is homotopy equivalent to omega C and chi plus 1. Why is this? Well, because C and chi is homotopy equivalent to M and chi. Oh, well, same as the loop spaces. The homotopy type of the Moore construction is the same as the homotopy type of C and chi. Now this is the same as omega B M chi, and this is sorry. Let me. Let me put just homotopy equivalences here to make the notation consistent with what we've been using so far. Okay, so omega B and K, what is this? Well, this is the same as C omega C naught and chi plus 1, and this is the same as omega C and chi plus 1 because well, by definition, loops lie in the same component as the base point. Okay, are there any questions? Now, well, the case k equals 0 is more difficult. So, what happens when k is 0? Well, we don't know, but to begin with, the set pi naught m comma 0 is not a group. well, by node m comma 0, well, to see y, let's take by node of cn comma 0. Well, what is cn comma 0? Well, it's the space of Clade submanifolds of 0, 1 to the nth. And what is the operation? Well, the operation is basically the disjoint union. The disjoint union of two non-empty submanifolds is non-empty. And on the one hand, and on the other hand, since all manifolds are inside the disjoint union of two non-empty submanifolds is non-empty, and the diffeomorphism type is of the underlying manifold is the same for all manifolds in the same connected component of Cn0. So if we have something which is not empty, we can't get the empty set by taking the disjoint union with that, and we don't get a group. We can't get nothing out of something by adding more things. Okay, so we need to do well. We need to use another model. The construction is as follows. Instead of and by the way, from now on, we'll assume d equal to and we will replace the monoid m and 0 by n. well, I will now briefly explain what the elements of this this monoid are. But the way the picture is okay. We'll talk about this version in more detail later, but so I don't want to get into too much detail at the moment. We consider surfaces with the first coordinate from 1 to a, where a is greater than 0, and we fix the behavior near the hyperplane. The first coordinate is 0, and the hyperplane the first coordinate is a. And we make some more assumptions, and we'll talk about those. We'll talk about those later. Basically, the boundary has 2 components, not 1, and we take juxtaposition in the first coordinate as the monoid operation. And so all these surfaces live in Rn. We'll take the union as n goes to infinity and call it m infinity, and what what do I need to assume? Well, another assumption is the surfaces are connected, and there's one more technical condition which I don't want to mention now, because it is unmotivated. It would be unmotivated with for us with what we know at the moment. Okay, so the genus could be arbitrary, and we take the limit as n goes to infinity, and we get something. I'll call this something m infinity. M infinity is a monoid. And again, a topological monoid. in a couple of weeks, we will prove the following proposition. As a space, M infinity or Bm infinity, the classifying space, is homotypically equivalent to C infinity 1. And what is C infinity 1? We haven't defined it. Well, it's the direct limit of Cn1 as n goes to infinity. The most miraculous thing in this formula is that the monoid operations are quite different. On the left, we have the connected sum, and on the right we have the disjoint union, which are clearly not the same. And so we will need to relate these two operations to each other. Okay, now we want to still be able to say something about monoids such that the pi naught is not the group. So we will use the group completion theorem. And by the way, the group completion theorem, I recall, is one of the topics for talks. It's not a massively difficult theorem. Okay, so suppose M is a topological monoid. I will now only state the version that we will need. In fact, the theorem is more general, but let's not get distracted. Suppose M is a topological monoid such that pi naught of M is isomorphic to Z greater than or equal 0. Which is the case for M infinity, pi naught of M infinity is the set of all non-negative integers, and the isomorphism is given by taking the genus. And what else? And we also assume that the operation on M, the monoid operation, is homotypic commutative. What does this mean? Well, this means that two maps which from M squared to M, the multiplication in the reversed order are homotopic. And this is again true for M infinity. Why? Well, for the same reason as that higher homotypic groups are abelian. We will see this in more detail when we get to this to these questions. Then we have the following isomorphism. By the way, before I state the isomorphism, I want to take M P to be the P's component. Where P is inside phi naught of F, which is the same as Z greater than or equal 0. Then I have an isomorphism between omega Bm, the homology of omega Bm, and the homology of Z cross cross the union of all MP. Now, the union with respect to which map? We take the union with respect to multiplication by by a fixed element of M1. Let's say right multiplication, although left would do. Now okay. just to be on the safe side, let's replace the union with the telescope. Although in our case this union will be a genuine union. Okay. Now,
is it an isomorphism over the integers or over the rationals?
Well, I think this this will be an isomorphism of the integers, but we'll see in more detail when we get there. So over Q. Maybe over Z as well, we'll see. Okay, now corollary. Well, let's forget all components except all components of the loop space except the one that contains the base point. Then we get just the union of the spaces MP on the right, and on the left we have the homology of the component of the unity of the loop space. Okay, are there any questions, remarks, and so on?
Why is there suddenly an isomorphism in homology and not the genuine weak equivalence, or just homotopy equivalence?
Well, we'll see it when we get to this point in the proof.
Oh yeah, it's trivial. Yeah, I'm sorry.
Are there any more questions? Okay, now well, we're almost done. Well, the proof is almost finished. We only need to collect all the statements we've seen so far. Okay. Well, the first step is to replace C infinity by the union of mg infinity. And we will also see that CG is a homotopy equivalent to M infinity G, which is again something that requires an explanation, because elements of CG have just one boundary component, and elements of MG have two. Okay, now the next step is to say that the result is the same as omega naught b m infinity. Well, this follows from the group structure theorem. Group completion theorem. Okay, well, this is the same as the homology of omega naught C infinity 1. And this is one of the propositions. Let's see which one. The proposition on page 3. Well, the latter is the same as the limit as n goes to infinity of the homology of omega naught Cm1. Why is this? Well, because omega naught and h connote with with direct limits if we take the direct limit topology. Now this is the same as the limit of omega n naught Cn. And this follows from again from one of the propositions. Let's see which one. Well, it's for k equal for k greater than 1, it's the proposition on page 2, and for k equals 0, it's the proposition on page 4. No, we've already used. No, we only need to since we already have k equal 1 here. We only need to use the proposition on page 4. And the result is the same as now we use now we use the same. Now we use the proposition that we proved in the first part of today's seminar. But unfortunately, the nodes have been lost. And finally, let's look at the answer we have here. The result is the same as basically the right-hand side of the Madsen-Weiss theorem, and we again use that homology and Lib spaces communed with direct limits. Okay, now well, basically this completes the proof. Are there any questions? Oh, sorry. There's a mistake here. It's page 2, not page 4. Okay. Okay. Are there any questions, remarks, criticism, or a combination of the above? Okay. Well, it looks like the answer is no. By the way, it looks like we're having problems again with the internet connection. Maybe it's the mouse. Hold on. Grisha, are you able to save the notes? For some reason
no, I don't think that I can save your notes, but
okay. I have looks like there's a problem with the mouse. Well, it looks like it's working, but okay, maybe I can do it with the keyboard.
should I stop the recording?
No. Oh yes, I've saved the notes using just the keyboard, which isn't much, but for me it's an achievement. Anyway, it looks like yes, I think we can stop the recording now.